In the last video, we took a look at this example of a hypothesis test involving the difference between two population means. This was the example looking at whether sleep deprivation affects a person's score on a memory test. And we went through the summary of that study, and we stated the hypotheses and checked the requirements. Step 3 is to test the hypothesis, and this time we'll use a t-test. So one method is to use the classical or test statistic approach, and for this approach it helps to draw out the t-distribution and then use table 7 to find the cutoff value for the region of the curve that represents an unusual study outcome. We want to make a note that this is a left-tailed test, since our alternative hypothesis had the less than symbol, and the alpha here is 0.05, and that's the area under the left tail of the curve. Here's what that would look like. We'll go to table 7, and we'll look for that critical cutoff value. To use table 7, recall that you need two pieces of information. You need the degrees of freedom and the area under the tail's curve. The degrees of freedom is n-1, that's 12 minus 1, which is 11. The area under the tail is 0.05. We'll look that up in table 7. Here's 11 degrees of freedom. Here's an alpha of 0.05. And it looks like they line up right here at 1.796. So according to table 7, the critical value is 1.796. However, that's not quite the correct value. Remember that table 7 only gives cutoff values for the right tail. So what we really found was this side of it, this cutoff for the right side. But since this is a left-tailed test, we want the cutoff for the left side. But it's okay because this curve is symmetrical, so the value that we want is just going to be the negative version of what we just looked up. So the actual cutoff for the left tail is negative 1.796. So here's what that looks like. Here's the cutoff for that left tail. The next thing is to calculate the test statistic. And in this case, the test statistic is a t-value. And we can use this formula to get that t-value. This formula, it looks different than what we saw before, but it's just because instead of this being x bar, this is d bar. And remember that d stands for the differences. So you're doing the mean of the differences minus mu d, the difference between the population means, divide by the standard deviation of the differences, and that's divided by the square root of the sample size. So one thing to note is that mu d, the difference between the population means, is always going to be 0. It's in the formula, but because the null hypothesis is that it's 0, this is always just assumed to be 0. So this you can just in effect make 0. Everything else we have calculated earlier. The sample size is 12. D bar, the mean of the differences, was negative 5.25. And then the standard deviation of the differences was 6.283 test points. Put all those values into the test statistic formula, and the result comes out to negative 2.8945. So the last thing is to determine whether the test statistic is inside the critical tail of the curve or outside. Our cutoff was negative 1.796, and our test statistic is on the inside of that. It's to the left of that cutoff. And that means that these studies' results are unusual and significant, and we would reject the null hypothesis. The second approach to conducting this hypothesis test is to do the p-value approach. So to find this p-value, you could use a calculator. And on the Casio calculator, these steps are the same steps as what you did in section 10.3 when calculating a t-test. So you go to your stat window, select test, which is F3, then select t, which is the F2, and then choose the 1s, that's F1. And so this time our inequality was less than for the alternative hypothesis. And the value of the null hypothesis is 0. In fact, this is always going to be 0 for this particular kind of test, because the null hypothesis, when you write it this way, is always 0. It's saying that the difference between the population means is 0. Then you put in the x bar. This is the d bar, but it means the same thing. And then you put in the standard deviation, put in the sample size. Similar for if you did this on the TI 83 or 84, go to your stat, go select tests, scroll down to the t-test, make sure that you're in the stats input, put in 0 always for the value of the null hypothesis, put in the mean of the differences, the standard deviation, the sample size, and then make sure to put in the direction of the inequality. So either way, when you do that, the p-value comes out to 7.2937 e negative 3. And remember that when you see that result in a calculator, it's scientific notation. It means 7.2937 times 10 to the negative third power. And if you convert that to standard notation, that's 0.0072937. What's the meaning of this p-value? Well, it's the probability that a random sample of 12 individuals would result in a mean of sample differences in memory test scores of negative 5.25 test points or less, and a standard deviation of 6.283 test points, assuming that the null hypothesis is true, that there's no difference between the population means of the memory test scores. But again, keep in mind, a p-value is a probability, and it's the probability of obtaining the particular results of this study, assuming that the null hypothesis is true. So now the last thing is we'll compare the p-value to the level of significance. For this study, our p-value was very small. It was smaller than the alpha. And because the p-value is less than alpha, that means that the study's results are unusual and significant, and we would reject the null hypothesis. And so the conclusion would be step 4. We want to explain our conclusion in terms of the alternative hypothesis. So we would reject the null hypothesis and say that there is sufficient evidence to conclude that the mean memory test score after a night of no sleep is lower than the mean memory test score after a night of full sleep. Alright, we'll take a look at one more part to this in our next video.